Dear students, welcome to the new lecture on measurements and instrumentation. Today we will be starting the module number 3. The first topic that we are going to discuss is resistance measurement. So, in the syllabus given, we are classifying the resistance measurement into low resistance, medium resistance, and high resistance measurement. Under low resistance measurement, we have two techniques. The first one is Kelvin's double bridge method and ammeter voltmeter method. And under medium resistance, again we have ammeter voltmeter method and Wheatstone's bridge. So under high resistance measurement, we have a loss of charge method, and we also have an application of resistance measurement, that is earth resistance measurement using Megger. Now we classify the resistors into low, medium and high based on the value that these resistors take. So the low resistance values will be having, or they are classified once their values are less than 1 ohm. From 1 ohm to 100 kilo ohm, we classify them under medium resistance, and from 100 kilo ohm and higher we have high resistance. And the copper winding in armatures, in machines, ammeter shunts in switches and contacts fall under low resistance category, and most of the common applications that we see around fall under medium resistance, like electronic circuits, carbon resistance, metal film resistors, etc. And when you think about high resistance measurement or high resistance values, for instance, we have insulation resistance of cables and wires which are having high resistance values higher than 100 kilo ohm in mega ohm ranges. So these are the crude classification of resistances. Now first we will take up the medium resistance measurement, then we will move on to low and high resistance measurement. And the first method is ammeter voltmeter method. Now we are given ammeter and voltmeter. So you can measure the value of an unknown resistance using a simple equation, V by I, where V is the voltage measured by the ammeter and I is the current that is measured by the voltage measured by the voltmeter, and I is the current measured by the ammeter. This voltage and the voltmeter and the ammeter can be connected in the circuit in two different ways. In the first method, we are connecting a voltmeter across a series combination of ammeter and the resistor. So you are connecting ammeter in series with the unknown resistor, and you are connecting voltmeter across it. And in the second method, we are connecting an ammeter in series with the parallel combination of voltmeter and the resistor. We are connecting voltmeter directly across the resistor, and the ammeter is measuring the current that is taken by both the voltmeters and the ammeter, unknown resistor. In the first case, the voltmeter will be reading the voltage drop across the ammeter as well as the unknown resistance. So there will be some errors that happen due to this particular nature of arrangement. We will discuss everything in detail. Now in the first case, we have a voltmeter which is connected across a series combination of ammeter and the resistor. So the voltage indicated by the voltmeter will be voltage drop across V, this ammeter as well as the unknown resistance. So here V will be given by VA plus VR. So the measured value, this is measured value, R1 will be equal to V by I or VA plus VR by I. So VA is given by I into RA. RA is the resistance of the ammeter, and VR is given by I into R, where R is the unknown resistance, or this R is the true value. Now R1 will be given by RA plus R, or measured value will be given by the true value plus the value of resistance of the ammeter. The true value can be given as measured minus the ammeter resistance. Now the relative error can be given as R1 minus R by R, or it is equal to RA by R. Now in this case, where do you use this circuit? The error can be reduced once the measured the true value is much higher than the value of the ammeter resistance. If R is much higher than RA, the error will be minimum. If RA is very small, the voltage drop across this ammeter also will be very small, so that the error introduced due to the ammeter also will be less. So you cannot change the resistance of the ammeter. What you can do is that if you are having a value of R much higher than RA, you can use this circuit so that your error will be minimized, and you can directly use this circuit to measure the unknown resistance using this simple equation V by I, so that your error will be minimum. Now moving on to the second figure, where ammeter is connected in series with the parallel combination of the voltmeter and the resistor. So here the ammeter will be indicating current IV plus IR. IV is the current taken by the voltmeter, and IR is the current taken by the, or current drawn by the unknown resistor. Now R2 is the measured value. Now the measured value is given by V by I. So I is given by IV plus IR. So V divided by IV can be taken as V by RV. V is the voltage across this voltmeter. V by RV, and or which is indicated by the voltmeter, and V by R gives IR. So from this you can simplify, or you can get this equation as R is equal to R2 plus R2 into 1 plus R2 by RV. Now when you take the error, you will have R2 minus R by R, which is given by minus R2 squared divided by RV into R. And if we consider the measured value very close to the true value, or when you replace R2 with R in this equation, you will get minus R by RV as the relative error. So in this case, the error can be minimized if the measured value, the resistance of the unknown resistor, is much smaller than the resistance of this particular voltmeter. If R is much less than RV, the error can be reduced. So if your resistance values R is much less than RV, what happens? The current through this RV will be very small, because the resistance is very high. So IV will be much smaller than IR. So most of the current that is indicated by the ammeter will be passing through IR, since the resistance, this circuit is having low resistance, so that you will be getting accurate results while you use this circuit to measure resistances. Now the suitability of particular method, the figure 1 or 2, depends on the relative values of resistances under measurement and the resistance of the meters. So with respect to resistance of the meter RA or RV, what is the value of R? So relative value will give you the suitability of a particular method. Now how do you choose this circuit 1 or 2? So the division point comes at a point where the relative errors given by, the absolute value of relative errors given by the two methods are equal. So that will be given by RA by R equal to R by RV. So you can say that R is equal to, from this equation, RV into RA, a square root of that. Now what is the concept of this particular equation? Now for resistance values with a value greater than that the value given in A, that is if you are having some unknown, some true value equal to 100 ohm, okay, and from this equation you are getting, this is a true value, from this equation you are getting R equal to, say, square root of RV into RA equal to 90. You are getting, you know the value of internal resistances of voltmeter and ammeter, so you get the value of 90. So in such a case, you can go for figure 1. And if your value is less than, if you are getting R value instead of 90, you are getting 190 RV into RA. So here the true value is less than this value, this particular value. So in such a case, you can go for figure number 2. Now we'll take an example and see how this can be justified. Now we have an example where your RV is a voltmeter, resistance is 6000 ohms, and resistance of the ammeter is 2.5 ohm. So voltmeter will be having high resistance and ammeter will be having low resistance. And from this you can calculate R using the previous equation as root of RV into RA as 122.5 ohm. And since I have taken this unknown resistor, I know the value of unknown resistor. So what I have done is that I know that the unknown resistor is having a value which is lower than this value. So I have used figure number 2 to make some measurements. So using the figure number 2, I have made some measurements. So the voltmeter is giving me 38.4 volt and ammeter is giving 0. Or indicating 0.4 amperes. and the voltmeter is indicating 38.4 volt. So these are the two indications that is given by the meters. So now the measured value is given by V by I, which is 96 ohms. So this is the measured value. Now what is the current that is flowing through the voltmeter? That is 38.4 is the voltage across the voltmeter divided by the voltmeter resistance RV, which is given by 0.0064 amperes. And once you get IV, I can find out IR. Since I is given, we know I is equal to 0.4. So once I is known, I can find out IR as 0.4 minus this value. So that will be 0.3936. Now the true value is given by the voltage. 38.4 is voltage across this resistor, that divided by IR. IR is here. So I get the true value as 97.56 ohms. Now the relative error, the percentage error will be given by 96 minus 97.56 divided by 97.56 into 100, which will give you minus 1.56 percentage. So this is the error that you get once you choose this circuit for this particular figure number 2 for finding out the value of unknown resistor. So if I use the same resistor, but if I use the circuit number 1, what will happen? Using figure 1, I am giving an input voltage of 50 volt, suppose, and again I am using the same voltmeter and ammeter with 6000 ohm and 2.5 ohm respectively as the internal resistance values. The true value I know that it is 97.56. Now what is the value of I? I can be given by input voltage divided by this resistance. So voltage across these 2 points, suppose I am calling it as A and B. Voltage across AB is 50. So 50 divided by the resistance of these two elements, that is RA plus R. It is 2.5 plus 97.56. This is a true value which will be giving you the current I. So the current indicated by the ammeter will be this value. So the measured value, here you are connecting this directly across 50 volt. So your voltmeter will be indicating 50 volt. So the measured value R will be 50 divided by the ammeter reading 0.4997, which will give you 100.06 ohms. Now the error will be true, measured minus true by true into 100. So that will be 2.56%. So compared to minus 1.56 or 1.1%, here you are getting 2% error if you are using this. So we know that based on this particular equation, if your value is less than this, if your true value is less than this value, you can go for figure number 2. So where your error is less. If you go for figure number 1, you will get the answer, but your error is more because you are getting a higher value, and again the error is more. Instead of 97, you are getting 100. So that's how you can choose or you can select between circuits, figure number 1 and figure number 2 to measure. Anyway, both the circuits give you almost accurate results, provided your accuracy levels of voltmeter and ammeter are fine or very close to the true values. And the second method that we are going to discuss is the Wheatstone's bridge approach, and this is one of the most commonly used methods for measuring of medium resistances. Here we have 4 resistors which are connected in a bridge manner, and here it is composed of adjustable resistors, and R is unknown resistor, PQ and S can be adjusted to adjust the galvanometer reading. So we are trying to balance this particular bridge by bringing the galvanometer reading to 0. Once by adjusting the resistor values, by adjusting P, Q or S, we can bring the galvanometer value to 0. Once the galvanometer reads 0, what happens? This potential at point D and potential at the point C will be equal. Once the current flowing through this is 0. Once the current is 0, this potential will be same. So once the potential is same, what I can say is that I1P, the voltage AD will be VAD will be equal to VAC. That is, I1 into P will be equal to I2 into R. Also, I1, since there is no current flowing in through galvanometer, I1 will be equal to I3 and I2 will be equal to I4. So that will be given by E divided by, E is the input voltage that is given to this bridge, E divided by P plus Q. I1, and I2 will be given by E divided by R plus S. So using these equations 4 and 5 and also this, using all the three equations, you can simplify it and you will be getting R is equal to P by QS, or a famous equation is P by Q equal to R by S. So the derivation is simple, you can just get the answer in 2 steps. So this is the well-known or famous equation P by Q is equal to R by S. So from there unknown resistance R can be found out. Now here the error due to inaccuracies in the indicating instruments. Here you are not using any ammeter or voltmeter to show any values. You are just using the galvanometer as a null element for identifying the zero values. So such inaccuracies can be eliminated due to the inaccuracies in indicating instrument. So such errors can be eliminated. Again, the balance condition is independent of the source voltage. Even if your source voltage is having a different value, the balance can be achieved by controlling the value of resistances. So this is used to measure resistance values in the range of 1 ohm to 100 kilo ohm, and the accuracy always depends on the quality of resistors that you choose. So thank you so much.